right, this is part 2 of looking at KSP problems. So just remember that our KSP is a solubility product constant, and all KSP is an equilibrium constant for a dynamic equilibrium that is happening between a undissolved solid and its dissolved ions. So it's looking at a saturated solution where there is excess solute in equilibrium with dissolved solute. So at the macroscopic level, at eye level, we're not seeing anything. But at the microscopic level, what we're seeing is some ions precipitating and some of the precipitate dissolving. So the third type of KSP problems that we're going to look at is predicting if a precipitate will form. So all it is really doing when we are predicting if a precipitate is going to form, all we're really doing is asking if we are going to get a reverse reaction. That's what we're looking for. Will we get a reverse reaction to happen? Now, you know from previous equilibrium problems that you compare the K equilibrium to Q to determine the direction that the equilibrium is going to shift. So we are just applying that now to a dynamic equilibrium between a dissolved or an undissolved solid and its aqueous ions. Now, for some reason, they like to give things different names. When you are determining if a precipitate is going to form, you are comparing the KSP value to Q, and in this case, they call Q trial ion product. Okay, so that's, for some reason, it has a new name. It is the same Q. It is calculated the same way we've calculated Q in the past, but it has a special name, trial ion product, because it is dealing with ions dissolved in solute or in solution. So we know from before that based on the relationship between Q and K equilibrium, which way the equilibrium will shift. If Q is greater than K equilibrium, the reaction goes in the reverse direction. So that's exactly the same situation here. If K is greater than KSP, if Q is greater than KSP, we get the reverse reaction. And because the reverse reaction is the ions forming a solid substance, when Q is greater than KSP, we get a precipitate. Okay, so that's a big piece here. When K is greater than QSP, we get a precipitate. So if our whole point is to predict if a precipitate will happen, what we really want to do is figure out the relationship between Q and KSP. So if Q is equal to KSP, there's no precipitate. The solution is saturated, so that means there's just perfect amount of solute dissolved in the solution. And if K or Q is less than KSP, the solution is unsaturated, which means the solution can handle more solute, and there's no precipitate. So really, what we are looking for is right here. Are we going to get a reverse reaction? To get a reverse reaction, Q has to be greater than KSP. So let's dive right into an example. Okay, so we're going to take a look. Our first example, determine if lead sulfate solid precipitate will form if the following is mixed and KSP is 1.8 times 10 to negative 8. So just remember, KSP, no units, just like K equilibrium. All right, so we are mixing 255 mils of 0.00016 mole per liter lead nitrate aqueous and 4.56 milliliters, or 456 milliliters of 0.00023 mole per liter sodium sulfate. So what I want you to notice right now is that we have two aqueous ionic compounds, and we are forming a solid product here, lead sulfate. The lead is coming from the lead nitrate, and the sulfate is coming from the sodium sulfate. So what we have is a double displacement reaction. So if we look at that right here, it's important that you get the balanced double displacement reaction. And now in this example, I'm giving it to you. So here's our balanced chemical reaction, and we are very, very interested in our lead sulfate. So we need to understand what we need to know in order to calculate Q is the concentration of the lead ion and the concentration of the sulfate ion. Because our dynamic equilibrium is between the solid lead sulfate and its dissolved ions. So the dynamic equilibrium that we're looking for is right here. We know that we do not need any information about the solid because we don't include the solid in our calculation. We need to know how much lead we're going to have and how much sulfate ion we're going to have in our solution. But the lead ion, the amount of lead that is going to be in solution is coming from the lead nitrate. And the amount of sulfate is coming from the sodium sulfate. So we have to use the initial information we have up here to figure out the concentrations or the amounts of lead and sulfate. So what we do is we make a statement that looks like this. You're always going to want to make this given statement. We know that the initial concentration of lead is going to equal the initial concentration of lead nitrate. Okay. This is because when lead nitrate dissociates, it dissociates for every 1 mole of lead or every 1 molecule of lead nitrate, 1 lead ion is released. Okay? Because there's 1 lead right here. So the initial concentration of our lead ion is going to equal the concentration of the lead nitrate. So it's 0.016 mole per liter. The initial concentration of the sulfate ion is going to equal the concentration of the sodium sulfate. Now, again, that's because when a sodium sulfate dissociates, every 1 sodium sulfate releases 1 sulfate ion. If we were after a sodium ion concentration here, we would have to multiply it by 2 because the sodium sulfate releases 2 sodium ions. All right, so we have our initial concentrations, but we have to take into consideration the volume of our substance that, or the change in volume that's going to happen when we combine these two solutions together. This is because you have 255 milliliters of 0.00016 mole per liter. So when you add that 255 milliliters to the 456 milliliters, your volume has changed, but your number of moles has not changed. So the concentration of your ions is going to change once you mix the two substances together because you changed your volume. It's like if you had a cup of water and you added a whole bunch of salt, and then you had a cup of sugar or a cup of water and you add a whole bunch of sugar. You have really salty water and really sugary water. And if you mix those together, it's actually going to be less salty because you are diluting it. So your concentrations of these ions are going to change once you mix the substances, once you combine these two volumes, because you are changing a volume, and concentration is number of moles over volume. So a quick calculation that you have to do is total volume. So you're just going to add up the two volumes that you are mixing together. And once we mix things together, we're having a total volume of 711 milliliters. And once you've done that and you've calculated the total volume that you have when you mix these two solutions together, you have to calculate the concentration of each ion after mixing. As soon as you mix them, the concentration changes. So this is a quick way to do it. We're going to start with the lead ion. So we have our lead ion, and we're going to use just conversion factor really easily. And we are going to go 0.0. I think I'm missing a zero. I am missing a zero. 0.00. Oh no, my children came home. You're going to go 0.00016 mole per liter. And then you can multiply it by its initial volume, so how much you started with, divided by the total volume. So the initial volume of lead solution that you started with is 255 mils, and then our total volume is 711 mils, and then you just do the math. Now, you don't have to convert the units to liters, because when you put a milliliter divided by a milliliter, these two units cancel each other out. We end up with a concentration of lead after mixing of 5.74 times 10 to the negative 5. Then we're going to do exactly the same thing for our sulfate ion. We're going to take the initial concentration we had from that sodium sulfate, and we're going to multiply it by 456 mils divided by 711 mils. So initial volume over total volume, and we get 1.48 times 10 to negative 4 mole per liter. So we had to do all of this work to get the ion concentrations in order to calculate Q. So at this point, we are at steps that are going to look familiar to you. We're going to write out our Q, and then we're going to substitute in our values. It looks like I am wrong on my, here we go, my work here. So lead ion, we calculated 5.74 times 10 to the negative 5 mole per liter, and times our sulfate is 1.48 times 10. This is really messy. Mole per liter. And we do our math. Now, one thing I want to point out to you is that I'm going to come back up here. When our lead sulfate dissociates, it's dissociating into one lead ion and one sulfate ion. So there's no coefficients. If there was coefficients, we would have to carry those to our equation for Q, but both of the coefficients are ones. So we do our math and we get 8.46 times 10 to the 9. Remember that Q is unitless, so we don't need our units here. And then all you have to do after that is compare your Q to your QSP. So our Q is 8.46 times 10 to the negative 9. Our KSP is, I should have written this out the way I do it in real time. Our KSP is 1.8 times 10 to the negative 8. So I like to write the numbers side by side. And then I like to put in the sign here. So 8.46 times 10 to negative 9 is actually less than 1.8 times 10 to negative 8. So our Q, so we make this statement here, since that's what this means, right? Upside down triangle. Therefore, Q is less than KSP. Therefore, no precipitate. Remember, to get a precipitate, you can only have your Q has to be greater than KSP. All right, so make sure you have this down. Hopefully you were pausing to copy as we went.